Here I'm going to describe the terms in the Excel spreadsheet that we can use if we want to calculate kinetic parameters using nonlinear regression, but it's on data that's obtained from a plug flow reactor. So on a separate screencast, describe the reasoning and the approach we use to carry out this calculation. Here I just want to discuss the setup of the spreadsheet and show what terms are there. And then in the subsequent screencast, show the actual use of the spreadsheet. So the rate expression that we're looking at to model a catalytic reaction is shown here. And just as a reminder, the two parameters, the rate constant, the absorption equilibrium constant. So let's look at a copy of the spreadsheet. So the two parameters we're trying to determine are indicated in yellow. These are the values we obtained after we did nonlinear regression. So in the spreadsheet, what I've done is I generated some data, and the data used these values for parameters. And then I added some noise to that data. And then I took the model and regressed, comparing the calculated data to experimental data. And I'll show you what I've done with that. Here's the pressure, temperature, gas constant, and then the feed concentration. This is in micromoles per cubic centimeter. The step size is the size that I'm going to use to step through the numerical integration. The volumetric flow rate we're actually going to change. So I put in 1 as a value, but as you'll see, that's our variable because experimentally that's what we varied. Now something I want to point out is we're doing a lot of calculations here. We're doing numerical integration, in this case for like 400 steps, and each of those steps has 5 terms to calculate. And then we're creating a table, so we're doing that 10 times or so. So the solver, when we run it, after we do that calculation, every time the solver iterates, it's got to redo the calculation with different parameters, so it can take more than a minute to get to the solution. And of course, depends how good our initial guess is. But as I explained, and as are listed up here, the K terms, the easiest way is to calculate K term for the first step, the 0.05 cubic centimeters, where here's our inlet at the volume of the reactor is 0. We calculate the 4 K terms, and then we calculate Ca from this term. So that's what each column is. And each row, so we just copy these cells down because we're stepping through increasing the volume. Down at the end of the spreadsheet, the volume is 20 cubic centimeters. That's the volume we're using in the calculation. Now the critical thing, the thing that makes this feasible, is to create a data table. So this is the data table. This is the cell that indicates what we're calculating. And this value is the cell I411. So that's the value of Ca at the end of the reactor where the volume is 20 cubic centimeters. And then the way the data table works, it will now use the volumetric flow rate first of 1, then of 1.1, and it'll calculate what the exit concentration is. And you can see as we increase the volumetric flow rate, and therefore decrease the residence time, then the concentration leaving the reactor increases, the conversion decreases. So this column is from our model for whatever values you put in for K and Ka. The next column, these are the experimental values that I created by taking the calculation for Ka of 0.1 and rate constant of 0.4 and then adding noise. Residuals are the difference between the calculated value and experimental value. So it's experimental minus calculated. And this column are these residuals squared because that's what we use to do our regression. So this column, this final cell here, the yellow cell, is the sum of the values in this residual squared column. That's what we want a regression to minimize. These are the actual residuals, the difference to show once we've done a fit how close we are to our measured values. Now we can use the data then to make a plot. The squares are the experimental values in the column I just showed you, and then the orange line is calculated from our model for the parameters that we obtained from nonlinear regression and shows the fit is good. The other graph that we can make that's useful is the residuals. And the reason we're interested in this because it shows us if we have a random distribution of errors. Of course, here, since these are not actual experiments but were generated, they're random. And if these were experiments, the kind of things we want to calculate would be the run number, namely, how many sets of one sign are there of the residuals. So, for example, here's a set, they're negative. Then a set positive, now a set negative, positive, negative, positive. So the run can be 3 or 4 with the same sign. All we're interested in is how many of these circled values are. Here there are 7, so that's certainly what we would expect. If we have 11 data points divided by 2 and add 1, that's the expected number. One number that will indicate we have a random distribution, and of course we do because it was generated. So in the subsequent screencast, we'll actually look at the spreadsheet to get a better understanding of how to carry out this calculation.